Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Google DeepMind. Joining the discussion is Ziga Avsec, who leads their genomics team. The central claim emerging from AlphaGenome is that biological complexity itself can serve as computational leverage rather than computational burden. The engineering approach here rejects the standard memory versus context trade-off entirely, treating the genome as a topological structure rather than a linear sequence. We'll examine the specific technical decisions that enabled this shift. Reading a book spanning millions of pages while simultaneously analysing the microscopic ink texture of every single letter appears physically impossible due to the limits of human focus. The team behind AlphaGenome claims they have destroyed this exact trade-off for the source code of life, creating a model that defies the fundamental laws of computational resource allocation. The destruction of the context versus resolution iron law stands as the first paradigm shift. In genomic modelling, Ziga Avsec identifies a historic, painful trade-off. You could either look at a very long sequence of DNA to understand the big picture, or you could zoom in to see high-resolution molecular mechanisms, but you could never do both. The computational memory required to hold a megabase length sequence at single base resolution is simply too massive for standard hardware. The team inverted this engineering logic. Instead of accepting the memory bottleneck, they sliced the genome into subsequences and processed them across multiple TPUs. The counterintuitive breakthrough here isn't just parallel processing. It is that these TPUs actively communicate with one another. By allowing the first processing unit to talk to the last one, they created a system where the model understands the global context of millions of base pairs while retaining the granular single base precision of a microscope. They didn't compromise. They engineered a way to cheat the memory limit. Regarding the fragility of multitasking in artificial intelligence, a second equally disruptive shift emerges. Common wisdom in machine learning holds that as you add more distinct, complex tasks to a model, the performance on the original tasks often degrades due to interference, a phenomenon known as catastrophic forgetting or task dilution. Natasha Latasheva and the team found the exact opposite. They took a model built for 1D DNA sequences and forced it to predict complex 2D modalities, such as splicing and contact maps. Logic dictates this added complexity should weigh the model down. Instead, they observed that adding these massive multidimensional tasks did not hurt the performance of the original modalities at all. The team believes this is because they are not actually separate tasks. They are measuring the same underlying biological reality. By forcing the model to understand the 3D folding of the genome, it actually reinforced its understanding of the 1D sequence. This suggests that in high-stakes biological AI, complexity is not a burden, but a stabilizer. The engineering heresies that made this possible center on data throughput. Tom Ward revealed a viewpoint that completely flips the narrative on big data. The industry standard assumes that training on massive genomic data sets requires building larger, faster, and more expensive data pipelines to handle the sheer volume of information. Ward's logic inverted this. He realized that while the data volume was massive, requiring 40 to 50 gigabytes of loading bandwidth, the information density was shockingly low. He found that for many modalities, the data was 99% zeros. The paradigm shift here is realizing that the bottleneck wasn't a lack of hardware speed, but a lack of intelligent compression. By treating the data as a sparse signal rather than a raw stream, they bypassed the physical limits of data loading. They didn't build a bigger pipe. They realized the water was mostly air. This philosophy of doing more with less extends to how they view the physical structure of the genome itself. Traditionally, DNA is viewed as a linear string of code, a long one-dimensional text. Jun Cheng and the team introduced an ontological shock by successfully modeling contact maps and splicing within the same architecture. They are essentially saying that to read the genome, you cannot just read the letters. You must understand how the book physically folds in three-dimensional space. Splicing involves bringing non-contiguous information together, meaning part of the code on page 1 might control an instruction on page 100. By incorporating contact maps, which capture the 3D folding of DNA in the nucleus, they are treating the genome not as a static library, but as a dynamic folding origami structure where proximity in space matters as much as proximity in sequence. This redefines the genome from a sequence problem to a topological problem. The displacement of the wet lab as the sole arbiter of truth represents perhaps the most jarring shift for the scientific community. There is a deep-seated belief in biology that computational predictions are merely rough guesses that must always bow to experimental data. Jun Cheng highlighted a specific instance where AlphaGenome recapitulated cancer-driving mutations found in wet labs, ranking them significantly higher than random controls. This implies we are crossing a threshold where the simulation is becoming high fidelity enough to rival physical observation. The model didn't just find patterns, it identified the specific mutations that drive cancer, effectively performing a virtual experiment that mirrored years of physical research. This challenges the ontological status of the experiment, suggesting that for certain genetic questions, the dry lab might soon become the primary discovery engine. The inversion of workflow logic completes the picture. In the field of genomics, high-precision variant scoring is notoriously slow, often taking minutes per variant and requiring massive dedicated GPU clusters. The assumption is that high-value science requires high-friction infrastructure. Tom Ward and the team dismantled this barrier by releasing an API that allows researchers to run these massive calculations in a simple notebook without installing drivers or owning a GPU. They moved the heavy lifting from the user's local machine to a parallelized on-device aggregation system in the cloud. This changes the definition of who can be a genomic researcher. It shifts the paradigm from science is for those with supercomputers to science is for anyone with an internet connection. They didn't just speed up the process. They removed the infrastructure requirement entirely. A consistent pattern runs through these technical decisions. The team refuses to accept the traditional boundaries between dimensions and resources. Whether it is collapsing 1D and 2D data into a single model or compressing massive data sets into sparse signals, they operate on the belief that biological complexity is not a barrier to be feared, but a structure to be exploited. If the source code of life is now readable, writable, and compressible like standard software, what happens when we start debugging it in real time? If you're interested in the video featured in this episode, click the link below to watch the original.